All right, let's go ahead and get started. Hope you like the new classroom. Hopefully we won't get thrown out. We'll just continue with our lecture and see what happens. So tonight we are going to discuss hypothesis testing. And this is really just an extension on concepts we've already gone over so far. And I thought about a couple different ways to teach this material. And I've decided that I want to start with a rather lengthy example. And this is an example that you'll be able to reflect back on if you look at the sort of the exercises in each section of Chapter 9. It's the initial exercise. It has to do with some rent in St. Louis. Has to do with some rent in St. Louis. And we're going to look at a long example of hypothesis testing from those examples. And then once we get done with that, hopefully we should have a good grip over hypothesis testing. And we'll have a chance to work through some problems and make sure you feel comfortable with it. So, hypothesis testing. The example I'm going to work with is, suppose you are in St. Louis and you are looking at various one-bedroom rentals, and someone tells you that the average rent for a one-bedroom apartment in St. Louis is $1,560. So, let's see. 1560. Hey, how you doing, fellas? All right. So, I don't know, some realtor, some rental agency tells you the average mean rent in St. Louis for a one-bedroom is $1,560. And for some reason, you don't believe them. And you want to test whether or not this is accurate. And you want to find some sort of system for doing that. So, how you might construct this is you might start off by saying, all right, Mr. Realtor, I'm going to start by assuming that what you're saying is true, and then I'm going to gather some statistical evidence and see if I can prove it to the contrary. So I might set up a question hypothesis test such as this. I might say, okay, I'm going to start with something I'll call the null hypothesis, and I'm going to notate it H with an O, and I'm going to say the mean of a one-bedroom apartment in St. Louis equals 1560. Fine. I'm going to assume that's true because you tell me. And then I'm going to gather some evidence and see if I can disprove that. And if I can disprove that, then I'm going to default to something I'm going to call the alternative hypothesis. Notated HA. And the alternative is that the mean does not equal 1,560. So I'm assuming the null hypothesis. We're going to take some samples and we're going to see if we have enough evidence to disprove and reject this null hypothesis. If we do, then the alternative hypothesis must be true. So the way we're going to do this is using techniques we've learned in class 1 through 3. We're going to think about random sampling. We're going to take a random sample, and we're going to see what we come up with. So, let's suppose we have a population of one-bedroom apartments in St. Louis. Every single one-bedroom apartment in St. Louis is in this population. It may be normally distributed. It may not. We don't know. But it has some sort of frequency distribution. Maybe it's skewed. We don't know what it is. But we're going to use the techniques we learned. We're going to take a random sample from that population. It's going to be more than 30. Right, so n is greater than or equal to 30. All right, and then we're going to analyze that information. But we know, because we took stats class, that if we were to do this over and over again, thousands of times, and we were to graph those sample means, remember we notate the sample mean with the x bar. We're going to graph all those sample means. What would the distribution look like? The graph of all those sample means?
Normally distributed.
Be normally distributed. And what would this frequency distribution be called? Don't blurt it out. Just think it into your head. I want everyone to get a chance to recall what this term is. The more you think about it, the more you say it, the less intimidating it becomes. So, question, what is this frequency distribution called of all the sample means? Think in your head. Okay, blurt it out. What's that? Close. The sampling distribution of the sample mean. Yes. Excellent. So, let's see. Sampling distribution of the sample mean. Sample mean. Okay. And we know that this frequency distribution, hey, how you doing? Hey, come on in, is going to be normally distributed. Because it's normally distributed, we know things about that. We know things about how the data will fall. We know things about the characteristics of this frequency distribution. We know that the mean will equal what?
0.
We could look at it as 0 if we're putting it in the standardized z-scores. So yes, that is along the lines of a true statement, but the actual mean of this sampling distribution of the sample means
X bar.
will be a number. All right? So we're taking samples of one-bedroom apartments in St. Louis, and we're going to come up with an average each time. What is it going to center around? What's the most common number we're going to get if we do this 1,000,000 times?
60.
Population mean, exactly. So we know the mean is 1560, and we know something about the standard deviation of the sampling distribution sample means. What do we know about that? I should notate this correctly. The sampling standard deviation of the sampling distribution sample means is this standard deviation sign with a little X bar next to it. I'll give you a hint. It's something divided by the square root of n. Yes. Standard deviation of the population divided by the square root of n. So, given that we know those things about it, we understand that there's going to be a way this breaks down in terms of number of standard deviations that the data might fall on either side of the mean. Like, what do we know about how much data will fall plus or minus 1 standard deviation from the mean?
68.3%.
Yes, exactly. Hey, come on in. Yes, we know that. 68.1 or 68.3% of the data will fall within 1 standard deviation. How about within 2 standard deviations?
95.5.
Yes. And 3 standard deviations is like 99.7. So, suppose we were to take a sample mean and we were to get one of those sample means that falls, let's do this. This is 1, and this is 2 standard deviations. Okay, we were to get one of those that falls above 2 standard deviations above the mean. So it's a really high number. What would we say about that? All right, how would we interpret that? We go back to the office. We go back to the person we said we didn't believe you. Well, how might we interpret this sample mean that falls 2 standard deviations above the mean?
Just one of the sample?
Yeah, it's just one of the samples. It's the one we did. we did a random sample of more than 30 people, and whoa, it came out to be whatever it is, 1605, whatever it was.
Not looking too good that hypothesis is happening.
It's not. What do you mean by that?
So it's or 95%. It's out of the 95%. So it's if that number was true, if I took it again, it's not looking good if I get one that goes far out like that.
Oh, okay. I like where you're going with this. One thing we could say is that happens 5% of the time. And I'm gonna where I think you're going with this, Justin, I'm gonna get to next. But we could say that's just one of those deals. We took a random sample, but in this case, all 30 or a number of those samples were high. Right? And if we were to take it again, it wouldn't be so high. Does everyone understand that? So this happens 5% of the time. We might also get a sample mean that is low, really, really low. All right, that happens 5% of the time. These two together, I guess, happen 5% of the time. So getting a really, really high sample mean happens 5% of the time, or excuse me, 2.5% of the time. And getting a really, really low sample mean happens 2.5% of the time. So if we are strict statisticians, we might say, well, this is one of those things that happen. Doesn't necessarily prove anything. The data we collected could be really high, could be really low. That's the way the normal distribution works. There's one conclusion we could draw from getting a really, really high sample mean and a really, really low sample mean. Now, what is the other conclusion we could draw from a really, really high sample mean or a really, really low sample mean? Now, keep in mind, one option is that's the way statistics works. It happens 5% of the time. 2.5% of the time it's really high, 2.5% it's really low. That's option one. That's the way it is. I'm looking for option two right now. What is the alternative to believing that?
We could calculate the probability of the difference between means.
We could calculate the probability of that happening, and it's and we know what it is. It's 2.5%. 2.5% that it's this high. 2.5% that it's this low. Right? It happens. A mean that extreme happens 5% of the time. That's option one. Option two.
95%.
Option two is that this mean is incorrect. So we need to decide how extreme our sample mean needs to be before we say there's such a low probability of that happening. I'm more comfortable just saying that this mean is wrong. Does that make sense? Nadia? Kind of making sense? Okay. So, we have two possibilities, two options. We collected this sample data, and if it were really, really extreme, we could say, well, this happens. That's the way the graph looks. It happens 2.5% of the time that high, 2.5% of that low. 5% of the time it could be something that extreme. Other option is we could say, that is so unlikely, I'm going to reject the null hypothesis, and I'm going to believe the alternative hypothesis. So let's put some numbers to this. Let's erase my crossed out 560. Let's assume that's still good. Mean equals 1560, sorry. let's put some numbers to our research. Let's suppose we go out, we take a sample of 50, and we get a sample mean of 1586. So, this is what we're working with. We've set up our null and alternative hypothesis. We have a sense of how this decision might be made. And we take our sample, we get n equals 50. Okay, and we get x bar equals, what did I say, 1585? 1586. Now we need to choose what we call a significance level. And a significance level is notated with this little sign here. A significance level. So let me read you what we mean by the definition of significance level. Significance level is the probability value that defines what we mean by unlikely, given a true null hypothesis. And I'll repeat that. If you want to jot it down, it's also in your textbook. And we'll just make sure we're comfortable with that before we move on. So let me read that again. Significance level is the probability value that defines what we mean by unlikely given a true null hypothesis. Significance level is the probability value that defines what we mean by unlikely given a true null hypothesis. So, I used the example a minute ago that's where we said if this sample mean falls outside of 2 standard deviations above or below the mean of the sampling distribution of the sample means, then that's fairly unlikely. 5% chance. We could say, all right, that's 5% chance happens. Or we could say, that's so unlikely that we're going to reject our null hypothesis. So let's assume for a moment that our standard isn't even that high. Let's take a significance level of 10%. So significance level of 10%. That's going to be double the thought process that we just went through. Thought process we went through is 5% was unlikely. But let's choose, for our example, a significance level of 10%. So what's going to happen is we're going to test this sample mean, and we're going to say, well, if there's a 10% or less chance of that happening, we're going to say, this is not true. And we are going to reject the null hypothesis, and we are going to accept the alternative hypothesis. So let's think about how that looks. So 10% chance. What that means is that, hey, come on. That means, so we're going to be looking for a 5% chance that we might get 5% chance that we might get a really high sample mean, or a 5% chance that we get a really low sample mean. So if our data, our sample mean falls in the top 5% or the bottom 5%, we have 2 choices again. And what are those 2 choices? Let me answer it because I've thrown a lot of confusing stuff at you. One choice is that happens 10% of the time. The other choice is, that's so unlikely that we're going to reject the null hypothesis and we are going to assume the alternative hypothesis. So, given this 5% in the bottom tail, 5% in the upper tail, we need to find what we call critical values. Those are z values above or below which we will reject the null hypothesis. So we need to find some z's, z values. Z values. All right, and these are going to be numbers. Numbers that we used before: 1.96, 1.65, 2.533, negative 1.65, negative 1.96. And we're going to set that up before we calculate where our sample mean falls. So, if we want to encompass 5% of the data below or 5% of the data above, what is the z-score that's going to be relevant?
1.65.
I'm liking the sound of that. Does anyone agree or disagree? 1.65? Okay, so if we get a z-score of negative 1.65 or lower, that's going to be important to us. Or if we get a z-score of 1.65 or higher, that's going to be important to us. So let's talk it through. If we calculate from our sample mean, and we get a z-score of negative 1.65 or lower, what are we going to take that to mean? Yeah, all right. It's 1.7 or 1.8 or 2 standard deviations below the mean. What's that going to mean for our hypothesis test?
Yeah.
We are going to reject.
Reject.
Yes, Justin's pointing down. We are going to reject the null hypothesis. Now suppose we get a z-score higher than 1.65. What will that mean for our hypothesis test? We're going to reject the null hypothesis. Because we're going to say, all right, granted, there's a 10% chance of that happening, but we chose a significant level of 10%, and we said that if anything with less than 10% of a chance happens, we're going to say that's too unlikely. That is our definition of unlikely, and we're going to reject the null hypothesis. So let's calculate what the actual sample means we might get, which would be below our critical value and above our critical value. So these z-scores, by the way, are called critical values. Critical values. Z-values. Okay. So let's crunch out our standard deviation of the sampling distribution and the sample mean, and then let's figure out what the actual numbers would have been, would be if we were below or above here. So I need to give you the standard deviation of the population. Assume we know it for now, and we'll talk about what to do if we don't know it. Standard deviation of the population is $100. Okay. So, standard deviation of the sampling distribution of the sample means equals 100 divided by the square root of 50 equals, who's got it for me? I've got it.
$14.14.
14.1. I like it.
Yeah.
Okay. It's important information for us. Standard deviation of this is 14.1. So what number, which is going to be 1.65 standard deviations above the mean, is going to be relevant? And what I'm looking for is a number in the neighborhood of 1560. It might be 1586, it might be higher, it might be lower. What is going to be the threshold where above that number we reject, below that number we do not reject? again, we're assuming that the null hypothesis, we're assuming that the mean of the sampling distribution of the sample means is 1560. So we need to add 1.65 standard deviations to that number.
Sorry, can you say that?
So we're going to assume that the mean of this is 1560. We need to add 1.65 standard deviations to that number to know where that critical point is. Where if it's higher than that, we reject. If it's lower than that, we do not reject. So you're going to take 1.65 times 14.1 plus 1560.
1583.
Okay. 1583. And how about on the low side?
Fifteen 37.
How much?
1537.
1537? Let me double check. Yes, it's about what I got. Okay. Good. So, all right. So now let's take a step back and remember what we're doing. We're trying to determine whether or not we believe this realtor when she or he says the average rent in St. Louis is $1,560. We said, nah, I think you're trying to sell us something. I don't know where you're getting the data. I don't believe you. So I'm going to set up a hypothesis test. I'm going to assume what you say is true. And I'm going to see if I find overwhelming evidence to the contrary. If I find evidence that would be so unlikely given that what you say is true, and if it is unlikely, if it's that unlikely, I'm going to reject that and assume the alternative. And then we had to make a decision. What do we mean when we say unlikely? We could have said 1%, could have said 5%, just so happens we said 10%. Then we went out and we took a sample, random sample of 50 apartments. We got a sample mean of 1586. And we know the population standard deviation of 100. We're assuming we know that. We'll talk about what we do if we don't in a moment. We set up our decision. Now what do we do? Are we ready to make this decision? We said that if the sample mean is below 1537, what do we do?
Reject.
Reject. What if it's above 1583?
Reject.
Reject. And what is it?
It's high.
1586. So what do we do?
Reject.
We reject. We reject the null hypothesis, and we assume that the alternative hypothesis is true, and we say, Ms. Mr. Realtor, we believe that the average is not 1560, and we have statistical evidence to back up our theory that you are wrong. Make sense? Right. Let's mull on that for a second. I'll get a drink of water. Yes. All right, any questions? We're going to stay on this for a while. We'll keep ruminating on it. Yes, you should.
So the sample mean is just used to compare with the result. The sample mean.
Oh, okay, yeah. This is our this sample mean.
Sample mean, yeah.
Yeah.
Just used to compare with the result.
Yeah. Well, once we set up the result, we'll compare. And we're going to look at it a different way because putting in these numbers is not as common of a way to do it, but I wanted to show you that way. To your question, let's do it a slightly different way. Let's cast our mind back to what we did in class 1 and remember how we established a z-score for certain males with a certain height. We said Michael Jordan has a z-score of 2.4, Randy has a z-score of negative 1.6. We calculated the z-score for a certain individual. We can also calculate a z-score for a sample mean. So let's calculate the z-score for this sample mean. And we'll call it the z-statistic. Okay? So we're going to do it the same way. So the z-stat equals the sample mean that we found, 1586, minus the
1560.
population mean, assuming it's true, 1560, divided by the standard deviation of our sampling distribution of sample means. 14.1 equals, what do we get when we crunch that out?
1.84.
Okay. So that is a z statistic, a z-score of 1.84. How does that fit in with our decision paradigm?
1.6.
Yes.
Above, it's on that right air end.
It's above. It's above what? 1.65. Right? It's right here. So it's in the reject area. So this sample mean, we went out, calculated, we gathered the data, we did it the right way with random sampling, so on and so forth. That returned a z-score, a z-statistic of 1.84. And we decided, before we even started this, that if we have a z-score above 1.65, we are going to reject the null hypothesis. We also said if it comes out to be less than negative 1.65, we're going to reject the null hypothesis as well. And this is the way that we will calculate. Hopefully the actual numbers just help frame that for you. And if you're ever talking to someone who doesn't have a really strong background or any background in statistics, you might bust out with this sort of logic if you're trying to explain something to them. But we will calculate this way pretty much all of the time.
And the significance level, what does it really mean? Is it like how, let's say I'm looking for a house, who gives me that significance level? Is it what I would accept? Is it
Yeah, it's what you can live with. Because we rejected this null hypothesis. But we may have made a mistake. What are the chances that we made a mistake in rejecting this null hypothesis? What is the percentage chance that we made an error? 10% chance of making an error. Remember we said there are two possibilities. This happens 10% of the time, option 1. Option 2 is, that's unlikely, so we instead are going to reject the null. How comfortable are you? How important is this? What is the cost of making that kind of mistake? What is the cost of not making that mistake? These are factors that you're going to want to weigh when you decide the significance level. Now something else will help us that is similar to the significance level. It is called the p-value. P-value. This is the exact probability. Let me read you the number so I don't confuse you with faulty words. This is the exact probability that given the null hypothesis, we would find a sample mean at least as unlikely as we did. The p-value is the exact probability that, given the null hypothesis, given the true null hypothesis, you could throw that in, we would find a sample mean at least as unlikely as we did. The exact probability that given the null hypothesis, we would find a sample mean at least as unlikely as we did. So we said, we know, that the chances, given our significance level of 10%, and given that we rejected this null hypothesis, we know that there's a 10% chance that we would have found something as extreme as that, if this were true. Well, let's actually find the exact probability that we were to find a z-statistic of 1.84 or higher, or 1.84, negative 1.84, or lower. So what we're going to do to find a p-value is we're going to look on the z-score, and we're going to say, how much data is above a z-score of 1.84, and how much data is below a z-score of negative 1.84. So we know, choosing our significance level of 10%, that there's a 5% chance we could get something really high, 5% chance we could get something really low. But now we want to know exactly where we stand with this 1.84. And it's going to be somewhere in here, because we know it's above 1.65, so it may be this much above, maybe this much below. So it's going to be less than 5% on each side. It's going to be less than 10% total. We just want to find out what it is, so we can give someone more specific information. Instead of saying there's a 10% chance that we made an error, we can get more specific than that once we have this z-statistic. How are we going to do that? We're going to look on the z-score, z-table, and we're going to look for 1.84. We're also going to look for negative 1.84. So go ahead and crack open the z-score. And the way I like to do this is I like to look at negative 1.84 first. And that's going to tell you how much data is below negative 1.84 a z-score of negative 1.84. Alright, so we're looking on the z-score for negative 1.84. How much data is less extreme than that? So we have the z-table open. Everybody got it?
Negative?
Yeah, you can either do negative 1.84 or positive 1.84 and tell me how much data is in that extreme tail.
32.0.
3.29%. Yeah, or Amanda, you were saying 0.0329, right?
Yeah.
Okay, so the exact probability of getting something this extreme in either direction, 3.29% on this side or 3.29% on this side. In determining the p-value, we need to account for both sides. It could have been really extreme low. It could have been really extreme high. So the p-value tells us the probability of getting a test statistic, at least that extreme, is 3.29 times 2. My color's consistent. Times 2 equals, what do we got? You should
6.5.
6.59?
8.
6.58. Okay. Percent. Okay. So instead of just saying, well, there's a 10% chance of getting something that extreme and incorrectly rejecting the null hypothesis, we can now say there's a 6.6% chance of getting something as extreme as we actually got. And we define that by calling it the p-value. The p-value for this sample mean, 6.6%. Any questions? Yes. No.
So the 3.29% is multiplied by 2 to represent both sides of the
Yes. Because we're going to look at this a little differently in a minute, but for now, all we're saying is that the realtor says the mean is 1560, and we think there's a good chance that that's wrong. We didn't say we think it's bigger, we didn't say we think it's smaller, we just think that that is wrong. So we could get a really extreme value once we do the sample mean, and potentially that happens. How often does it happen? Well, 3.29% of the time it's that high, 3.29% it's that low. In either case, we would have rejected the null hypothesis. Yes?
You'd use the negative, but if you use the positive, then you would just subtract 9.67 from 1, and that would give you 3.3.
Oh,
Whichever
yeah.
one you use, right?
Yeah, exactly. So when you look at the positive 1.84 on the z-score, it tells you 90, what is it, 96, this, 100% minus this. And that's telling you how much of the data is below 1.84, 96 and change percent. And so that's why I like to look at the negative first. It's just easier to visualize. Okay, so we're going to stay with this example, and we're going to think about changing the significance level. We're going to say, hey, 10%, there's a good chance that we could go out on our sampling day, and, there's a 1 in 10 chance that we could get data which would be misleading, which would cause us to go back to that realtor and say, you're wrong, and we might be wrong. There's a 1 in 10 chance of that happening. So let's say we want to be a little more confident than that. Let's say we want a significance level of 5%. We only want a 5% chance of making that kind of mistake. So let's read you our analysis at the 5% significance level. Okay? Now, not a lot is going to change. The z-statistic is still going to be the same. The p-value, I'll give you a heads up, will stay the same because the z-statistic doesn't change. The critical values and the sample mean guide numbers will change, however, because we're now setting up a more stringent test. We need a higher burden of proof before we reject the null hypothesis. So let me erase these numbers. The mean will stay the same because it's still the same population. We're assuming that the sampling distribution of the sample means has the same property of centering around the population mean. The standard deviation will stay the same population. What will change are the critical values. We are now at the 5% level. We only have a 5% chance of making a mistake and incorrectly rejecting a true null hypothesis. The question is, what critical values, what numbers on that Z table do we need to put in here? Last time we had 1.65. Question now is, what do we need instead?
1.96.
1.96, positive 1.96, and negative 1.96. Because if you look up, let me write those down while we're thinking. Negative 1.96, positive 1.96. If you were to look up negative 1.96 on the Z table, how much of the data, remember 1.65 encompassed 5% of the data on the low end, what would 1.96, how much of the data would be below negative 1.96? 2.5%. So there's going to be 2.5% on the low side. Similar, on the high side, there's going to be 2.5%. Let's see, 2.5. High side, 2.5. And then, as we just talked about, if we were to look up 1.96 on the Z table, it's not going to say 2.5%. It's going to say something else. 97.5%. Because that's just the way the table's constructed. Okay. So, this is all we need to now make our decision at the 5% significance level. We've done the same sampling. That didn't change. We've calculated the Z statistic. We know the mean of the sampling distribution, sample means. We know the standard deviation. We've set up our critical values. We are now ready to make our decision. And what is our decision? So, what's your name again, Paul?
Phil.
Phil. That's right. Sorry. You were gone last week, so
Yeah.
out of sight, out of mind. Phil.
You would accept it all?
Okay. We say it a little differently than that.
You would reject the alternative?
We would not reject the null hypothesis. We're not saying the null hypothesis is true.
I see.
We would fail to reject the null hypothesis. Because remember when we started this whole thing? We said we're going to assume what you say, Ms. or Mr. Realtor, is true unless we find overwhelming evidence to the contrary. And we define overwhelming by less than 5% chance of that happening. And in this case, we did not find it. So we failed to reject the null hypothesis. Now, to Phil's point, we found a sample mean that was higher than the realtor told us. So we kind of want to say, well, what you told us was wrong. But we set a higher standard for ourselves, so we can't quite say that. Okay, any questions on that? This is going to be very simple. We're going to do the same thing with a slightly different significance level. We're going to say, before we go back into that realtor's office and get mad, we want to be darn sure. We want a significance level of 1%. So we're going to go storming into that realtor's office, and we're going to be mad And we're going to know that there's only a 1% chance that we made a mistake. There's a 99% chance the realtor was lying to us. There's a 1% chance, and I'm sorry, that's wrong. We can't say there's a 99% chance that there was lying to us, but we can only say there's a 1% chance that we made a mistake. Most of this stuff stays the same. The thing that changes are the critical values. We're going to need to look on the z-table. And we're going to need to find a certain amount of the data on the extreme edges. Now, what percentage of the data is going to be on the extreme low? What percentage of the data is going to be on the extreme high in this iteration of our hypothesis test? Ready? Yes. All right. 0.5%, also known as 0.005. 0.5%. Okay, so we need critical values.
Negative 2.58.
Negative 2.58.
And positive 2.
Positive 2.58. Okay? So we set ourselves a pretty high standard. We need to find something so extreme before we're willing to go out on a ledge and say you're wrong. And in this case, did we meet that high standard? We did not. We found a test statistic of 1.84. We needed one of 2.58 or higher, or negative 2.58 or lower, before we make a strong statement, because our significance level is, there's such a high standard, low significance level. So in that case, we failed to reject the null hypothesis. We cannot make that statement. Now, notice in these last two iterations, the p-value did not change. We still had the same test statistic of 1,586, which came out to a z-stat of 1.84, which came out to a p-value of 6.6%. And depending on what we chose for our significance level, that determined whether or not we accepted or rejected. If the significance level was higher than 6.6%, we rejected the null hypothesis. If our significance level was lower than 6.6%, we did not reject the null hypothesis. Make sense? All right. So we're going to stay with this example, kind of, but we're going to look at it a slightly different way. We're going to say, gosh, Ms. Realtor, you told us that the mean rent for one bedroom in St. Louis was $1,560. Yeah, I've been hearing a lot of numbers, hearing a lot of prices. I think it's actually higher than that. That's what I think. Before I just wanted to say that you're wrong. Now I want to say that it's actually higher. I think the mean rent in St. Louis is higher than $1,560. That's what I want to test now. I want to just look at it from one side of the equation and conduct what we'll call a one-tail hypothesis test. So we're going to go through the same sort of process. Let me just erase some of this. We may have to do it again, but that's fine. Okay? I am going to give you the benefit of the doubt the same way I did last time. I'm going to say, I assume what you say is true. That the mean rent for one bedroom in St. Louis is around $1,560. But I'm going to frame it differently. You think, I think it's higher. So I'm going to set up an alternative hypothesis where I think the mean is greater than 1560. I think the mean rent of a one bedroom is higher. Right? That's my alternative hypothesis. And I'm going to need overwhelming evidence to prove that. And the way I'm going to set this up is I'm going to assume the opposite. I'm going to assume that the mean rent is equal or less than 1560. So less than or equal to 1560. So I've still constructed a hypothesis test that encompasses all possible outcomes. The null hypothesis, the mean is less than or equal to 1560. The alternative hypothesis, which is what I'm thinking I might be able to prove, is that the mean is greater than 1560. And let's go back to a 10% significance level. Let's take the same type of sample. Let me interview more than 50 people in this sample. Let me see what I come up with. And let me think about what I can say if I'm only concerned about proving that the mean rent is higher. So if I'm only concerned about the mean rent being higher, then essentially there's only one area where I could get it wrong. There's only one little section, one tail, one of these two, where the chances of something like that happening would cause me to make the wrong conclusion. And it would be the probability in this high tail, in the higher end tail. There's some chance of me going out, gathering this data, and interviewing or selecting a bunch of apartments that cost more, that cost a lot more than the average. And there would be a certain percentage chance, we'll decide what we want that to be, where I could say, well, that happens 5% of the time. That happens 10% of the time. If I go out and I find a bunch of low-cost apartments, then I know without even thinking about it that I cannot reject the null hypothesis. So if I go out and I collect a bunch of sample data and say the sample mean comes out to be 1545. 1545. Sorry, we can't read that. All right, so the realtor told me the mean rent in St. Louis was 1560. I properly collected data. I found a mean rent of 1545. Am I anywhere near saying that the mean is higher than you told me? Do I have any possible evidence of proving that? Yeah, because my mean was lower than the realtor told me. So the realtor told me 1560. I went out and I collected a bunch of data. I came out with 1545. I'm like, okay, maybe you're right. 1560. Sounds fair to me. I need a sample mean, above 1560 before I can even think about storming into that realtor's office and saying that you were wrong. So this data below the mean, right, that's not something that's going to lead me to making an error. If I collect a low sample mean, then I'm just going to fail to reject. Where I might get myself into trouble is if I find a high sample mean, I might have to say, well, there's a 5% chance of that mean randomly being this high, or there's a 10% chance of that mean randomly being this high. So when we conduct a one-tailed hypothesis test, we concentrate the full significance level in either tail. And in this case, it's going to be in the upper tail. So we're going to be looking for 10% of the data. 10% of the time, we might find a mean that randomly is that extreme. If we want to be 10%, and we want a significance level of 10%, which means the maximum possibility of us making a mistake and rejecting a true null hypothesis is 10%. So this changes our critical values. Is everyone with me so far? Yes?
10% just on the right tail.
10% just on the right tail, because if data on the left tail doesn't apply. All right, that's low, you win. We can't even come close to rejecting the null hypothesis. And we want to know the percentage chance of us making a mistake and rejecting the null inappropriately. So, next question is, what in this case will be our critical value? What z-score, above which is there 10% of the data, below which is there 90% of the data? Critical values. Values.
Negative 1.29.
Okay, negative 1.29. All right. Tell me about the positive first. 1.29. Okay? That's the important critical value to us, 1.29. Why do I not care about negative 1.29?
Because you wouldn't be able to reject their.
You wouldn't tell me, I wouldn't be able to say the realtor's wrong. I need a z-score above 1.29 in order for me to reject the null hypothesis that the mean is less than or equal to 1560, and accept the alternative that the mean is higher than that. 1.29. So let's crank out our test statistic. We're going to crank that out the same way we did last time. We have a mean. We have a, let me erase this, 1545. The data we collected was a sample mean of 1586. Assuming what the realtor told us is true, the mean of the sampling distribution of the sample means is 1560. So let's do it. All right, we've got 1586 minus 1560 divided by standard deviation. Standard deviation doesn't change. It is the population standard deviation divided by the square root of n, which is the same as our example last time, divided by, what was it, 14.1? All right, and it's going to give us the same thing, right? Which is 1.84. 1.84. Sorry, 1.84. 1.84. Okay, we have all the information we need to make our decision. And what decision do we make? We reject the null hypothesis. We decided before we started this that if we get a z-score of above 1.29, that's good enough. We're going to reject the null hypothesis, and we're going to leave the alternative, which in this case is a different question than we asked at the beginning of class. In this case, the alternative is that the mean is higher. We're making a slightly different statement. Phil?
So this is only for a one-tail test, or specifically the right tail?
It's a one-tailed test.
So
We,
one
yeah,
tail.
we could do it. We could do it the opposite way.
Right.
We could say, you know what? I think you're wrong. I think it's lower,
Okay.
and then we would just have everything except reversed. Yes.
You did everything reverse with the -1.29?
Yeah. We wanted to set it up that way, and if we said, you know, we think it's lower, and we came out with a sample mean of 1586, we could just right off the bat say, oh, okay, no go. We don't even need to crank it out. We know it's above the mean,
Yeah.
so we know it's definitely not significantly lower, so much so that we can go back to the realtor and say that we think you're wrong. Okay. Let's go through the same process we went through with the last question. Let's adjust our significance level. This 10%, this is the chance, or actually, wait a minute, I'm sorry. Let's calculate the p-value for this test statistic, for this z statistic. What are the chances of getting something at least this extreme in this hypothesis test? Now, in this case, we mentioned that we don't care about anything below the mean. If it's below the mean, it's a no-go. If we get a sample mean that's below 1560, we're not going to use that to make any statements that are going to get us into trouble. We're only going to storm into that realtor's office if it's above the mean and significantly above the mean. So, in that case, how that works is we don't need to double the area under the curve to find the p-value for a one-tailed test. All we need to think about is what are the chances of getting a sample mean that is that high or higher. And when we looked at our z table, we found that a z-score of 1.84 was 0.96, whatever it was, remember? And it meant that 3.29% of the data was above that test statistic. 3.29%. That, in our one-tailed test, is the probability of us making a mistake and wrongly rejecting the null hypothesis. So the p-value in this case, p-value equals 3.29%. Make sense?
Yes. Because it's one tail, so we're not
Yeah.
right back to
Because it's what?
like one tail, so that needs to be right back to.
Exactly.
Yeah.
Exactly. Our only chance of walking into that realtor's office having made a mistake is if we get something on the extreme high side. And that happens 3.29% of the time. How often do we get a test statistic? 1.84 or higher? 3.29% of the time. So it could have been one of those things that happens 3.29% of the time. It's a possibility. It's also possible that what the realtor told us was wrong. Let's adjust the significance level. Recall last time when we adjusted the significance level, none of the calculations on this side changed. The only thing that changed were the critical values. So let's look at a significance level of 5%. Let's say 10% yeah, I'm really not comfortable with 10%. I want a maximum 5% chance of making a mistake. So I want a significance level of 5%. Chances of me getting this wrong are 5%. Granted, I'm still going to have to go to sleep at night and say, well, you know, an extreme test statistic like that happens 5% of the time. But that makes me sleep easier than having to say, well, that happens 10% of the time. What will change will be our critical values. This is a one-tailed test. All we care about is the area under the curve on the tail in question. In this case, all we care about is the upper tail. So we want to find the area under the curve, the top tail, the upper tail, 5%. Where's that 5% mark? Where, yeah, stuff that extreme happens 5% of the time. By stuff that extreme, I mean we get a z-score that high or higher. And you can still use the same trick. You can look on your z-table for the 5% mark on the negative, and then just know that it's identical on the other side, because that's what a normal distribution looks like. Or you could look under the z-table for the 95% of the data is less than that on the positive side. 1.65. Correct. 1.65. Okay, that is our critical value for this hypothesis test. Alright, null hypothesis, the mean is less than or equal to 1560. Alternative, the mean is greater. We established a significant level of 5%. We did this sampling, 50 people, came out with 1586 as our sample mean. We know the standard deviation is 100. We know the test statistic still comes out to be 1.84. Now we are ready to make our decision. And what is that decision? Lewis? Either reject or fail to reject. Help us out, Dan Rennie. All right, Phil, what do we do? We have this test statistic of 1.84, and we just determined that our critical value is 1.65. We can reject the null hypothesis. Because our null hypothesis that the mean is less than or equal to 1560. And we got something more than that. So much so that it is in the top 5% of unlikely things that might happen. Now it could be, on one of those unlikely things that happened, but we decided, we're going to believe what the realtor told us was not true. We're going to reject the null hypothesis. Now, notice that when we went from a significance level of 10% down to 5%, the p-value did not change. And what does the p-value tell us again? Right, the p-value gives us more specific information of exactly how likely a test statistic of that extreme or more extreme, how likely that is of happening. And a minute ago, we said our significance level is 10%. And what did we do? We rejected? We rejected, right? Okay. Now we decreased our significance level to 5%, and we got a higher critical value, higher standard of proof, but we did not decrease it so much so to overtake to be less likely than our already established p-value of 3.3%. We already said there's only a 3.3% chance of this happening. So we could take a significance level lower and lower and lower. Until we get to 3.3%, we're going to reject. Speaking of which, let's call our significance level 1%. Alright? I want a 1% significance level. I only want a 1% chance of making a mistake when I walk into that realtor's office. So without doing any calculations for critical values, tell me, are we going to accept or reject? Yeah, I shouldn't have said accept. Are we going to reject or fail to reject? Yeah, we can't reject it because we only want a 1% chance of something that extreme happening randomly. And we already decided that there's a 3.3% chance of this test statistic happening. Now, knowing that we're going to fail to reject, let's go ahead and put the critical value down for a significance level of 1%. We already know we're not going to reject the null hypothesis because that's just too stringent a standard when the data we have only happens with that level of frequency. So we need 1% of the data in the upper tail. What is the critical value, aka z-score, that we're going to use in that case? So we want a critical value, 5% of the data is above it, 95% of the data is below it. No, I lied. 99% of the data is below it, 1% of the data is above it. It's the critical value we want. Someone close?
2.37.
How much?
2.37.
Yes, 2.37. It's going to be a higher critical value, a higher burden of proof before we reject the null hypothesis. Make sense? How is this feeling? Comfortable? Yes.
Just to make it clear for me, as long as the critical value is above the z-stat,
Yes.
then you reject.
Then we do not reject.
You fail to reject.
Yeah, fail to reject. We need overwhelming evidence with this z statistic. Z-stat. It needs to be significant before we're going to say it causes us to reject this null hypothesis and accept B.
So in this case, we reject it because that's higher than the z-stat.
In this case, we do not reject because we only have 1.84 in our z-stat, and we've established with a 1% significant level, we have a higher burden of proof. So we do not reject. We do not reject unless, the reason we reject is if our sample mean falls into this area. Falls into that area where it's kind of unlikely that that happens. And we've established what we mean by unlikely by choosing the significance level. So, just, well, I don't want to rush on. So let's just be comfortable with that for a minute. Because this z statistic is lower than the critical value, we do not reject. We're going to go out and sample, and if we find a very high or very low, potentially, z statistic, then we're like, bingo, that's unusual. Right? That is in one of the extreme edges of this frequency distribution. And it might be grounds for rejecting the null hypothesis random.
So when the critical value is lower than the z-stat, then you reject.
Yes, that is correct. lower than the test statistic. So I would focus your thinking around the Z statistic. You may hear me call it test statistic or Z statistic, or in a minute I'll call it the T statistic. Question is, how extreme is that? Is it 3? Is it 1? I remember if it's 1, that's in that 1 standard deviation. 68% of the time it's going to be in that range. If it's 2, right, 95.5% of the time it's going to be within that range. If it's 3, right, then we're getting into an extreme scenario in which it's rare that we would have a Z stat that extreme. Okay, I wanna, how do I wanna do this? All right, I wanna do one more part to this example before we take a quick break. I want to think about what we would do if we did not know the population standard deviation. We do not know the population standard deviation. This standard deviation, we don't know what it is. If we don't know it, what do you think we do? I'll give you a hint. Very similar to what we did in the previous classes.
T state.
Yes, I heard the word T. We're going to make 2 adjustments to account for the fact that we do not know. One, instead of using population standard deviation, we're going to use the sample standard deviation. So out of the 50 people we sample, we're going to calculate the standard deviation among those 50 points of data. And if you recall, as far as the math, we're going to divide by n-1 rather than n, which is going to give us a sample standard deviation that's going to be a little bit higher. The other thing we're going to do is we're going to use the T distribution, which, as you might recall, is a little bit shorter and a little bit fatter in the tails. So this is our normal distribution. The T distribution might be something like this. So we're going to have to go a little bit further out to get the 68% of the data. A little bit further out to get the 95% of the data. A little bit further out to get 99.7% of the data. Now, I mentioned a whole bunch of times that if we're taking a sample and we use a sample size above 30, we can assume that the sampling distribution of the sample means will be normal. But if we're using a sample size less than 30 and we don't know the population standard deviation, then we don't know that the frequency distribution of the sampling means will be normal. We don't know this. I don't know if I stressed this last time. We don't know unless someone tells us that the population from which we took the sample itself is normally distributed. And they stress that a little bit more in this particular chapter because it's good practice to start thinking about using a smaller sample size and creating a wider confidence interval. So for a number of the problems, they'll tell you the population, even though the sample size was less than 30, the population from which we took those samples was itself normally distributed. So instead of this not normally distributed population, I'm going to say that this population that we took these samples from was itself normally distributed. And then I don't have to worry about the appropriate sample size. So we're going to conduct a one-tailed test, assuming we do not know the population standard deviation. But we're going to be throwing a softball. Someone's going to tell us that the population from which we take this data is itself normally distributed. So let's say we're trying to prove the same thing. The realtor tells us, hey, the average rent of a one-bedroom in St. Louis is $1,560. We say, you know, I've been doing some checking, and I think it's more than that. I think it's more than $1,560. All right, now suppose you do some sampling. You still follow random sampling guidelines. And instead of a sample size of 50, you're, for whatever reason, are forced to take a smaller sample of 20. You construct a sample mean of 110. The sample mean is typically going to be a little bit bigger than the population mean. And you come up with a sample mean of 1598. 1598. Okay. We still have the same null and alternative hypothesis. We think that the average rent is more than 1560, but the realtor tells us no, it's equal to 1560. So we're going to set up a null hypothesis of the average rent being equal to or less than 1560. Because if it's less, then fine, we don't really care about that. What we're trying to prove is that it's more. Everyone with me so far? So let's crunch out our t statistic for this information. We know, because we are told that these came from a population that is normally distributed, that the sampling distribution of the sample mean has all the same characteristics. The mean equals 1560. Standard deviation, standard deviation of the sampling distribution of sample means equals, this time we're putting in the sample standard deviation divided by the square root of n, which is 110 divided by the square root of 20, which equals, someone want to fetch that out for me? 22.4? Okay.
Oh no, sorry.
24.6. Okay. Fabulous. So let's now calculate our t statistic. We're going to calculate it the same way we calculated the z statistic. We're going to take our sample mean, 1598, t stat equals 1598 minus the mean, 1560, divided by our standard deviation, 24.6, and what does that come out to?
1.5.
1.54. Okay. And actually, I got a little ahead of myself. What have we not done yet? Right. Significance level and critical values.
Yes.
So, fine. Let's say the significance level is 10%. Now, is this a one-tailed or two-tailed test?
One tail.
One tail? Fantastic. And which tail are we concerned with? The upper tail or the lower tail?
Upper tail.
The upper tail. We're looking for a t statistic that is really significant on the high side. If it is, then we get to storm into the realtor's office and say, you were wrong. We are confident. In fact, we think there's only a 10% chance that we made an error. So we now need to look and determine our critical value. So we will crack open our T statistic textbook table. And what we're looking for is we're looking for the T-stat above which lies 10% of the data, below which lies 90% of the data. And remember, there's one thing we need to do with the T-stat before we begin, which is determine the degrees of freedom.
19.
So degrees of freedom, df equals n minus 1 equals sample size of 20. 20 minus 1 equals 19. So now we're cracking open our T distribution. We're looking under 19 degrees of freedom. And we want area in the right tail of 10%. Okay, 1.3, how much? 1.328, right? It looks right? Yeah, okay. So our critical value, 1.328. 1.328. Okay. Now, we've already calculated the T-stat. So we are at this point ready to make our decision.
Reject.
We've got a T-stat of 1.54, and we have a critical value of 1.32. Selena, we accept or reject? We've got an extreme T-stat. It's more extreme than our critical value. So we reject. We have found overwhelming evidence to reject the null hypothesis. So we reject. Very last thing I want to do is think about the p-value. Very last thing I want to do before we take a break and practice on these problems is think about the p-value for this T-stat. All right. P-value equals. Now, we're going to need to use our T distribution table just to give us an estimate. Now, if you have your T distribution, go ahead and crack it open and look at the line with 19 degrees of freedom. Now, we determined a minute ago that the area in the right tail was the 10% of the area in the right tail was above 1.328. Now, we've got a T-stat of 1.54, which means that this 1.54, it falls somewhere above this line, which is represented by 3.28. It falls maybe here. So we know that it's going to have an area, it's going to have a p-value of less than the 10%. We don't know anything else besides that yet. So what I want to direct your attention to is the next column over on 19 degrees of freedom. You can see that the t-stat is 1.729. So 1.328, 10% of the data is more extreme. But the one column over is 1.729, which represents the 5% mark, where 5% of the data is more extreme. And we know that our t-stat falls between those two. So we know that the p-value exactly is going to be somewhere between 10% and 5%. And how we figure that out is we'll just put it in Excel or a calculator that has that capability. And I think you'll have an assignment where you'll get to practice that. And you'll put, the number in. You'll put a couple pieces of information to give you the exact p-value. Okay, so let's take a break. Gosh, it's 8:07. Let's come back at 8:20, and we'll just finish off with some examples to try to make sure you're comfortable with this. I'll see you at 8:20.